Welcome back, everyone, for another deep dive. Today, we are going to be exploring something I think a lot of people are at least a little familiar with, quadrilaterals.
Right.
And more specifically, we're going to be looking at parallelograms, rectangles, rhombuses, and squares.
Mm-hmm.
And to guide us on this story, we have a chapter from a math textbook.
Oh, yeah.
It's full of all the good stuff: definitions, theorems, proofs, examples.
Those are the best parts.
Yeah, but as always, we want to kind of cut through all that technical jargon and try to pull out the core understanding,
Right.
like how these shapes relate to each other and some of those cool, like, ha-ha moments.
Mm-hmm.
We don't want to become geometry masters, but just get a good grasp on the basics.
Yeah.
So maybe the best place you start is with the parallelogram.
Okay.
Like, what is it? What is the foundation that we're going to be building all of this other stuff on?
Well, the basic definition is pretty simple. It's a four-sided shape, a quadrilateral, where both pairs of opposite sides are parallel.
Okay, so we can all kind of picture that in our heads, right?
Yeah.
Just two sets of parallel lines connected at the corners.
Exactly.
Now, one of the first big things that the textbook reveals is this idea that if you take any parallelogram and you slice it right down one of its diagonals,
Okay.
you end up with two triangles.
Right.
And Theorem 8.1 tells us that those two triangles are always congruent,
That's right.
which is kind of cool.
Yeah, so to explain why, let's imagine we have a parallelogram called, ABCD.
Okay,
And we draw the diagonal AC. This divides our parallelogram into the two triangles ABC and CDA.
gotcha.
Now, because the opposite sides of the parallelogram are parallel, we have pairs of alternate interior angles that are equal.
Okay.
So when the parallel lines BC and AD are crossed by that transversal AC,
Right,
the angles BCO and AC are equal.
gotcha.
And similarly, AB is parallel to DC, so with AC again as the transversal.
Yeah,
Angles BAC and DCA are also equal.
okay.
And then, of course, AC is a side that's shared by both triangles.
Right, they both have that same line segment.
Exactly. So we have two angles and the side between them that are equal in both triangles, and that's what we call angle side angle, or ASA congruence.
Okay.
Which means the triangles ABC and CDA are congruent. They're identical.
So really you're saying that at its core, a parallelogram is just two congruent triangles kind of stuck together.
That's a great way to put it.
And because of that, because those two triangles are identical, all of their corresponding parts must also be equal, right?
Right.
Which brings us to Theorem 8.2, which states that the opposite sides of a parallelogram are always the same length.
Yeah.
So AB is going to be equal to DC, and AD is going to be equal to BC.
Exactly. It's a direct consequence of that underlying triangle structure.
Okay, now Theorem 8.3 kind of flips this whole idea on its head. It asks, well, if you start with any four-sided shape, any quadrilateral, and all you know is that each pair of opposite sides is equal in length,
Okay.
does that automatically mean it has to be a parallelogram?
Right. And it turns out the answer is yes.
And the textbook gives us a hint that the proof uses side-side congruence, or SSS.
Right. So if you take this quadrilateral and draw in a diagonal,
Okay.
you create two triangles, and if the opposite sides of the quadrilateral are equal, that means all three sides of these triangles are equal.
So they're congruent.
Exactly. And if they are congruent, that means the alternate interior angles created by the diagonal acting as a transversal must be equal.
Gotcha.
And equal alternate interior angles mean that the opposite sides are parallel.
Which is the very definition of a parallelogram.
That's right. It comes full circle.
So we have this really handy way to identify a parallelogram. We just need to know that the opposite sides are equal.
That's it.
Okay, so we've talked about sides. What about the angles?
Okay.
Theorem 8.4 says that in a parallelogram, the opposite angles are also equal.
Right. And if you picture a parallelogram in your head, you can almost intuitively see why that's true.
You kind of can, yeah.
And to explain it, we can go back to those parallel lines and transversals.
Okay.
So consecutive angles in a parallelogram, like angles A and B or B and C, they are supplementary. They add up to 180 degrees
Okay,
because they're interior angles on the same side of a transversal.
gotcha.
And if angle A is supplementary to both angle B and angle D, then angles B and D must be equal.
Okay, because they both have to add up to 180 when combined with A.
Exactly. And the same logic applies to the other pair of opposite angles.
Makes sense.
And then Theorem 8.5 gives us the reverse of this. If you have a quadrilateral and you know that each pair of opposite angles is equal,
Mm-hmm.
then it must be a parallelogram.
Oh, okay.
And the proof, as the textbook mentions, involves using the fact that the sum of the angles in any quadrilateral is 360 degrees.
Right.
And this, combined with the equal opposite angles, means the adjacent angles have to be supplementary, which then implies parallel lines.
Okay, so the opposite side rule and the opposite angle rule.
Right.
Two pretty straightforward ways to spot a parallelogram.
Exactly.
Okay, so we've covered sides and angles. What about the diagonals?
Okay, yeah.
You know those lines that connect opposite corners? Theorem 8.6 states that the diagonals of a parallelogram bisect each other.
That's right, meaning they cut each other perfectly in half at the point where they intersect.
Okay, so if we imagine our parallelogram OBCD again, and we draw those diagonals AC and BD,
Mm-hmm.
they are going to cross each other at some point. Let's call it O.
Okay.
And what you're saying is that point O is going to be the exact midpoint of both of those diagonals.
Exactly.
So AO is going to be equal to OC, and BO is going to be equal to OD.
Right.
Okay, now how do we know that's always going to be true?
Well, the key, again, is in those congruent triangles.
Okay,
Remember, AB is parallel to DC, and AD is parallel to BC.
Yeah.
So we have alternate interior angles that are equal.
okay,
Like angle ABO is equal to angle CDO, and angle BAO is equal to angle DCO.
gotcha.
Now, we also know that opposite sides of a parallelogram are equal, so AB equals DC.
Right, we established that earlier.
Right, so now if we look at triangles AOB and COD, we have two angles and the side between them that are equal.
Okay,
So using angle-side angle, or ASE congruence, we know those two triangles are congruent.
gotcha.
We can do the same thing for triangles AOB and COD, proving they're also congruent.
So all four of those little triangles are congruent.
Yep, and that congruency tells us that the corresponding sides must be equal, meaning OA equals OC and OB equals OD. So the diagonals bisect each other.
Okay, so once again, those congruent triangles are the key to unlocking this property.
They really are the workhorse of parallelograms.
Now, naturally, there's a converse to this. If you have any four-sided shape and you know that its diagonals cut each other in half at their point of intersection, does that mean it has to be a parallelogram?
And the answer is yes. That's theorem 8.7.
Okay, so if we know that OA equals OC and OB equals OD, that's enough information to say for sure that it's a parallelogram.
That's right, because if those line segments are equal, then triangles AOB and COD are congruent.
By side angle side, because we know that angle AOB and COD are equal since they are vertical angles.
Exactly. So we have two sides, and the angle between them being equal, that's say-S congruence.
Okay,
And this congruence means that angle ABO equals angle CDO, since they're corresponding parts of congruent triangles.
gotcha.
And those equal angles are alternate interior angles, which proves that AB is parallel to CD.
Okay,
A similar argument using the other pair of triangles shows that AD is parallel to BC.
so both pairs of opposite sides are parallel.
Exactly, meaning we've got ourselves a parallelogram.
All right, that's a really good explanation of those first few theorems.
Thanks.
So we've established a pretty solid foundation for parallelograms.
We have.
Now let's move on to some of their more, I guess you could say, specialized relatives.
Okay.
Like the rectangle and the rhombus.
Okay.
So let's start with the rectangle. Its definition is fairly straightforward. It's a parallelogram that has at least one right angle.
That's all it takes. Just one right angle.
And the cool thing is, as example 1 shows, if one angle is 90 degrees, all of them have to be 90 degrees.
It's true.
And we know this because consecutive angles in a parallelogram are supplementary. They add up to 180 degrees.
Right.
So if one angle is 90, the one next to it also has to be 90 because 180 minus 90 is 90.
Mm-hmm.
And then, since opposite angles in a parallelogram are equal, that means all four corners end up as right angles.
Like a chain reaction.
Yeah, exactly.
Now, the textbook also throws in exercise 1, which suggests that if the diagonals of a parallelogram are equal in length, then it must be a rectangle,
Oh, okay.
which is an interesting link between the diagonals and those angles.
So just knowing that the diagonals are equal is enough to force those corner angles to become 90 degrees.
When combined with all the other parallelogram properties, yes.
That's cool.
Okay, let's move on to the rhombus.
All right.
The textbook doesn't give an explicit definition at first, but uses it in example 2, where it's described as a quadrilateral with all four sides equal in length.
Okay, so it's like a square that's been kind of squished.
That's a good way to visualize it.
So example 2 then goes on to prove a really interesting property of rhombuses.
Right.
It says that the diagonals of a rhombus always intersect at a right angle.
Yeah, they are perpendicular.
Okay, so let's break down why that has to be true.
All right, let's say we have a rhombus called ABCD.
Okay?
We know all the sides are equal. AB equals BC equals CD equals DA.
Right.
And because it's a rhombus, it's also a parallelogram, so its diagonals bisect each other,
Okay,
meaning they cut each other in half at that intersection point O. So AO equals OC and BO equals OD.
gotcha.
Now let's focus on two adjacent triangles like AOD and COD.
Okay,
We know that AO equals OC, OD is shared by both triangles, and AD equals CD because all the sides of the rhombus are equal.
right.
So we have side-side congruence, or SSF, for those two triangles.
Meaning they are identical.
Exactly, and that means their corresponding angles must also be equal, so angle AOD equals angle COD.
Okay,
But those two angles, AOD and COD, they also form a linear pair. They lie on a straight line, so they have to add up to 180 degrees.
right.
And if two equal angles add up to 180 degrees, then each one must be 90 degrees.
So those diagonals are cutting each other at a right angle.
Precisely.
Now, the textbook also mentions that the diagonals of a square are both equal in length and bisect each other at right angles,
Right.
which really highlights that connection between all these shapes.
Mm-hmm.
Because a square is both a rectangle and a rhombus,
Right.
it has 90-degree angles and all four sides are equal. So it makes sense that it would have both of those special diagonal properties.
Exactly. A square inherits all the best characteristics.
Okay, so we've explored parallelograms, rectangles, rhombuses, and we've seen how their properties work.
Mm-hmm.
Now, the textbook gives us a few examples of how these properties can pop up in other geometric situations.
Okay.
Like example 3, which starts with an isosceles triangle and the bisector of one of its exterior angles. And through a bunch of steps, it proves that a certain quadrilateral formed in that process ends up being a parallelogram.
Right.
And it's pretty cool how the initial conditions, like the equal sides of the isosceles triangle, lead to equal alternate interior angles,
Mm-hmm.
which then go fill the requirements for a parallelogram.
Exactly. You start with one thing and it leads you to something unexpected.
Yeah. Okay, then we have example 4, which takes us to a world with two parallel lines intersected by a transversal.
Okay.
And it shows that if you bisect all the interior angles formed by those lines,
Right.
the points where those bisectors meet will form a rectangle.
Yeah, every time.
So it's like connecting parallel lines and angle bisectors to rectangles.
And again, the proof probably involves showing that the resulting quadrilateral is a parallelogram with one right angle, which is the definition of a rectangle.
Okay, cool. And then there's example 5, which is kind of surprising.
Oh, yeah.
It shows that if you start with just any old parallelogram and you bisect all 4 of its interior angles, the points where those bisectors intersect will always form a rectangle.
It's a really neat result.
So no matter what your parallelogram looks like, if you do that angle bisector thing, you'll always get a perfect rectangle inside.
Yep, it's guaranteed. And the proof likely leverages the fact that consecutive angles in a parallelogram are supplementary.
Okay.
When you bisect supplementary angles, the resulting adjacent angles add up to 90 degrees, which then leads to each angle of the inner quadrilateral being 90 degrees.
And since the opposite sides have to be parallel because we started with a parallelogram, that means that inner shape has to be a rectangle.
Exactly.
Right, so we have explored parallelograms, rectangles, rhombuses, and we've even seen how their properties can show up in other geometric contexts. Now, the textbook introduces another really important idea, the midpoint theorem.
Right, one of the classics.
Yeah. And Theorem 8.8 describes a pretty simple but powerful relationship in any triangle. It says that if you find the midpoints of any two sides of a triangle and connect them with a line segment, that line segment is going to be parallel to the third side of the triangle and exactly half its length.
Yeah, it's amazing how such a simple concept has such broad implications in geometry.
And the textbook mentions that the proof involves extending that midpoint connecting line and then using congruent triangles to show that you've actually created a parallelogram.
Right, and once you have the parallelogram, the rest of the theorem just falls into place.
Okay, and as we've seen a couple of times already, there's also a converse to this theorem.
Of course.
Theorem 8.9 says that if you have a triangle and you draw a line through the midpoint of one side so that it's parallel to another side, that line is going to automatically bisect the third side.
It's like a guided path through the triangle.
Yeah, it's like you don't even have to worry about finding that exact midpoint on the third side. The parallel line does it for you.
Precisely. And again, the proof probably uses congruent triangles, using those parallel lines and the midpoint to show that the two smaller triangles created are identical, which then leads to the conclusion that the third side is cut in half.
Now, example 6 shows a really cool application of the midpoint theorem.
What is it?
It says that if you connect the midpoints of all three sides of a triangle,
Okay.
you end up dividing the original triangle into 4 smaller triangles that are all congruent to each other.
Right. Creates this really neat symmetry.
Yeah. And to prove this, you can use Theorem 8.8 to show that the little quadrilaterals that are formed inside a triangle are actually parallelograms.
Right.
And then because the diagonal of a parallelogram always divides it into two congruent triangles, that means all four of those smaller triangles end up being congruent.
Exactly. It's a very elegant and visual result.
Okay. And finally, example 7 takes the midpoint theorem and extends it to a situation with three parallel lines crossed by two transversals. And it proves that if those parallel lines intercept segments of equal length on one transversal, they will also intercept segments of equal length on the other transversal.
It's like a proportional relationship between the segments.
Yeah, exactly.
And this example just highlights how the midpoint theorem, even though it seems pretty simple, can be used to prove these more complex geometric relationships.
Okay, so we've covered a ton of ground here. Maybe now is a good time to go over the key takeaway.
That's a great idea.
And conveniently, the textbook provides a nice summary at the end of the chapter.
Perfect.
So, just to quickly recap, we saw that the diagonal of a parallelogram divides it into two congruent triangles.
Mm-hmm.
And we went through all the main properties of parallelograms. Opposite sides are equal, opposite angles are equal, and their diagonals bisect each other.
Right.
We talked about how those diagonals behave in rectangles, rhombuses, and squares, with the rectangles having equal diagonals, rhombuses having perpendicular diagonals, and squares having both.
It's like the square has it all.
Yeah, exactly. And we also talked about how the converse of all those statements is also true, which is pretty neat.
It is.
And then finally, we looked at the midpoint theorem and its converse, seeing how they connect those midpoints of a triangle's sides to the third side.
Right.
I don't know about you, but it's really amazing to me how these seemingly abstract geometric relationships are so deeply ingrained in the world around us.
Oh, absolutely.
It's not just theoretical stuff in a textbook.
Right.
This is the foundation for all sorts of things in engineering, architecture, and even the design of everyday objects.
Yeah, a good understanding of these properties allows us to build structures that are both strong and efficient.
Exactly.
Like the parallelogram, for example, it's super stable because of that rigid triangular structure inside of it, which makes it really useful in architectural designs.
Okay, so as we wrap up this deep dive into quadrilaterals, I want to leave you with one final thought to ponder.
Okay, shoot.
How do you think these properties that we've explored in 2 dimensions might change or evolve when we start thinking about these shapes in 3-dimensional space?
Oh, that's a good one.
Like what kinds of new shapes and relationships emerge as we move from the flat plane into the world of solid geometry? It's a whole other layer to explore.
It really is. Something to think about for sure.
Well, that brings us to the end of today's deep dive.
Mm-hmm.
Hopefully, you're walking away with a better understanding of these fundamental geometrous figures. Until next time, keep that curiosity burning.
See you then.